Hi, I'm Craig Price with Surface Water Solutions. Excited to be your host today for our webinar covering HEC-DSS, the data storage system. An introduction to one of the programs that is becoming increasingly more prevalent in the industry in exchanging data back and forth. And so we're excited to have Martin Jacobs on board as our expert presenter today. But before we dive into that, one of the things that always impresses me on these webinars is the global extent in today's world. As we look around, it's some of the things that people are dealing with, and some people doing it really tough at the moment. Just seeing this global snapshot, hundreds of registered attendees today around the world. Welcome. We're excited to have you on board and to be interacting with you. So today we have got Martin Jacobs from pitt&sherry, who's a chief hydraulic engineer, and from the Corps of Engineers. Absolutely thrilled to have Karl and Matt on board. They've got deep experience. The developer of DSS and the DSS view, Karl, and then Matt, who is the core water management system team leader. If you want to turn on your cameras briefly, just say hi. Where are you coming to us from today? So I think Martin, you're out in Brisbane, right?
Yeah. Good morning from Queensland here.
All right, bright and early there. And then Karl and Matt, you guys are in California. I assume everybody's working from home these days. How things going there?
Yeah, good morning. We can actually see the sunshine's out now. The smoke was hiding it, but now it's back.
That's right.
Good,
and,
yes.
And I've come to the office. I'm a sacrificial lamb. But yes, we're enjoying the fresh air and sunshine.
All right. Well, it's great to have you guys on board. We'll hear from Karl and Matt later on after Martin's presentation. They will be watching the Q&A line, so keep those questions coming. These are the ones who wrote the book on the subject, I guess. So in the background, we've got the experts on board. Those of you who joined us through the HEC-RAS channels, this is very relevant. You'll see Martin walk through some of the coordination between HMS and HEC-RAS, and the future and the developments that are coming into this are extraordinary. And the bigger we get these data sets and the more data, time varying and spatially varying data we've got, you've got to be able to organize your data in a way that makes sense, and it's compact, and you're able to interrogate it. And that's what we're here to hear from Martin on. So with no further ado, Martin, if you want to start sharing your screen, and we'll turn it straight over to you for our presentation. Over to you, Martin.
Thanks very much. Yeah, my name's Martin Jacobs. I'm the principal hydraulic engineer with pitt&sherry, with about 30 years experience in consulting overall. Talking to you about a beginner's guide or an introduction to HEC-DSS. We're going to have a look at why there's an HEC actually, and why HEC-DSS, how you use it and what it is. I'm going to assume that the audience here has got some familiarity with hydrology and hydraulics, including HEC-RAS, and I'm quite encouraged to see a lot of HMS users there, not essential. And one thing which is becoming increasingly important, of course, is familiarity with GIS systems, and particularly projections. If you think about it, rain is geographically distributed, it's temporally distributed. So this is all about how the rain interacts with the landscape in a geographic context. And I want to make a big shout to the guys at the Hydraulic Engineering Centre, particularly Thomas Brower and Michael Bartels, who have been gracious enough to respond to my various emails about how to do something, and ironing out a few bugs here and there with some of the latest developments. I'd like to run through some of the material that I did with the Stormwater Queensland a couple of months ago, which is all about point data. But one thing which is really new, and it's so new that I had my first successful trial on Friday, is the use of gridded rain. We've got that up and running within the Australian context, and that's a really exciting development and a game changer. So why the Hydraulic Engineering Centre? Now I want to ask this question because it produces the software to obviously address a number of hydraulic and hydrological problems. I'm an English person. I work in Australia, so coming across the US Army producing hydraulic and hydrological software is a bit strange for me. Why are they doing it? Well, it's fundamentally because they're the federal agency for the US, dealing with major federal projects such as the Panama Canal and the Columbia River Treaty. There's the Columbia River, and after the Columbia River there on the right. And again, these are projects which have profound or difficult questions to do with hydrology and hydraulics. And as I'm going through my business, looking at different projects and different scales, perhaps and some of them are the same, I'm thinking, well, if I've got a problem, then it's possibly that HEC has already looked at it. And so it's worth looking through what HEC has done before trying to design my own systems and my own programs and so on. In other words, if you've got a hydrological or hydraulic problem, it's likely that HEC might have looked at it. They might not be able to, but it's a good place to look in terms of trying to find a solution. A feature of the federal agency is that the HEC shares its software with the world for free, which means we can use it for free, but we're not entitled to support from HEC in the same way as a paid user. And so one of the big caveats about this presentation is that most of what I'm doing is self-learned, although, as I say, I'm very grateful for the guys at HEC for responding to my emails and pointing me in the right direction. And they'll chip in at the end with their own views as well. Why should we be interested as users? Well, data wrangling is a significant dimension of hydrological and hydraulic analysis. We're dealing with long-term rainfall series, gauge data, all sorts of data. We've got to be able to configure that information, maybe manipulate it, get it into a format which we can store, which we can make available to the programs. And sometimes we've got to do things to the data to make it usable. We've got to transfer the data from one HEC program to another. What got me into this was a couple of years ago, I was looking at a long-term continuous simulation project for a local government here, looking at 130 years of data with 30-minute time steps. When I'm talking about long-term simulation, I know ARNR 2019 talks about it as well. I'm talking about very long-term simulation, perhaps an awful long period of time, much more than 10 years. The good news is instantaneously DSS system can easily handle that sort of length of data. We're talking about 13 million points in the rainfall. So we need the rainfall, start with rainfall. We apply that to a hydrological model and the evaporation, of course, get the results in terms of flows coming off the catchments, apply them to a hydraulic model, combine the flows with tide and other factors and hydraulic structures and so on. And from there we can do flood frequency analysis and duration analysis. This particular project was all about the efficiency of draining lowland cane fields down in the tidal zone. So was the drainage of those fields being affected by development upstream, even though the development upstream had a detention basin associated with it? And we can do that over a very long period of time. The logistics of this project were such that I had to chunk it down into 65 two-year simulations, and so you got 65 hydrological models, 65 hydraulic models, and so on. You had to run them all off each other for various scenarios, and had to stitch all that together. And the way to stitch it all together was to use the DSS. So HMS is outputting to DSS, HEC-RAS is reading the results from DSS and outputting that results to further DSS files to give a result. Now things have moved on a little bit since my presentation a couple of months ago. We'll hand over to Matt at the end of this presentation, but if you jump onto the HEC website, you'll find that the release version for DSS View is 2.0.1. The gridded rainfall that I'm going to talk about is in beta versions 3.0.1. And this morning, I believe, and I'll let Matt explain this a little further, HEC has uploaded the RTS, which has got a lot of that functionality already rolled in. So you're right on the cutting edge here on what's coming out of the HEC. So what is it? When you open up a DSS view file, you'll see something like this. You've got the file name at the top, there's some part names and a bunch of records down here below. It's a data system that stores paired data. Fundamentally, it stores time series and uses real dates. Now this is something that you'll need to understand. So we're looking at Gregorian calendars and leap years, and if ever you've done these manually, you'll know that that's quite a difficult thing to code. DSS View and DSS uses Java, which has got some really good data objects. You might have noticed, for instance, the series that I did for that long-term series starts in 1889. If you use Excel, for instance, Excel cannot do dates before 1900, and it thinks that the year 1900 is a leap year. So you don't want that those sort of artifacts appearing in your analysis. We're talking about time series. These are date plus rain, or date plus flow, date plus stage. And you can also put in water quality parameters as well, and other things, date with pH or EC, electrical conductivity, pollutant concentration, and so on. It also deals with other paired data. So it'll store your stage and elevation data for dams and storages, and it stores statistics such as flood frequency analysis, stage duration analysis, and so on. And as I said earlier, the thing which we'd like to talk about is date plus gridded rain, which is a very exciting new development. Now, these are notes on DSS View 2.01. They give you the idea of the structure of what we're dealing with, and it's slightly different in 3.0, although 3.0 is a beta version. DSS View is the program which accesses the DSS file, which is this database. So you don't actually save things, which is a bit, you've got to get used to the workflow. It's just an interface between you and the database. There's also in version 2 the DSC file, which is a catalog file, and that tells you, that gives you a catalog of what's in the DSS file. I'm showing this on screen here because what you've got is a tag, and then you've got a record path name. We'll come to path names shortly. But the path name is a container that DSS throws the data into. So it collects the data in these containers, and they're usually time-oriented, and sometimes in months, and you'll see a sort of duration there. And this is what you'll see in your, if you look in Windows Explorer, you'll see this kind of thing here. You'll see a DSS file and a DSC file associated with it with version 2. Things have changed a little bit in version 3. As I said, that's a beta version at the moment. Now, the part names tell you an address for the container that the information goes into. You don't necessarily have to fill them in, but you drive yourself mad if you don't. There are some that are quite prescriptive, and there are some which are more freeform. So part A, for instance, might be the name of the river catchment. B is a specific location, gauge, town, crossing. C is the part type. Usually that's read by some of the other programs. The precip inc is the rainfall. D is usually starting date. E is time interval. It can deal with irregular intervals and regular intervals. Irregular, of course, you've got an irregular time step, and regular means that it's got a regular time step. And part F is kind of free form for additional identifiers or notes. Note that there are no quality codes, but DSS will deal with null values. So when you're downloading, say, a rainfall record or a gauge data, you'll often get quality codes with that. DSS can't actually import the quality codes, but you might want to put a threshold to say everything below a particular quality code or above it, depending on how the thing's configured, ignore and just substitute with a null value. So you're not putting zeros in instead of nulls. Part names for common time series. This is on the DSS website, but it gives you an idea. Precipitation or rainfall. You've got different options here. Again, I use the precipitation increment a lot because it's the incremental precipitation during each time step. Instantaneous accumulation is the cumulative precipitation at the end of the time interval. So that's always going up, if you like. Discharge is instantaneous, stage is instantaneous. Evaporation is also a cumulative thing, and that's ET in millimeters. So here's where I hope things work, because I'm going to show you how to get data into DSS. This is the way to get started, of course, so that you can start to play with what DSS is and what it does. Okay, so how do you import data into DSS? What I've got here in front of you is a text file showing, which has been downloaded from the Silo website with some rainfall and other data in it. This is the raw file that's come straight from the website. Usually what I would do is import this into a spreadsheet and use a spreadsheet function to process the data. Basically I want to split the data into day, month, year, time, and then the data itself. I'm using rainfall, but this is the same for all the data that you're going to use. And then copy that into a text file. The reason I like text files is because you can't really mess with them once they're set up. So it doesn't need to be a rainfall file, it can be any file, but we've split it into this format. So you've got one row per record, got the day, month, year, time, and then the data. So how do we get that into DSS View? I've got one record in here already. I'm just going to repeat what I did earlier. We go to, we set up the file, which is, you have to set it up to start with. DSS will not operate unless it's got a DSS file to act on. So you just file new, create a new file, and then import. So the data, you go to data entry, import, time series data, and then navigate to your text file. It will actually import from Excel spreadsheets as well, but I prefer, as I said, just text files. You open it, and what it will do, it will read the start of the file, and come up with a data entry screen here. Now here's the stage which is a bit difficult to describe in the documentation, because what we're going to do is right click on each of these columns. It's important to do that to separate the day and the month, because the computer doesn't know if 0407 is the 4th of July or the 7th of April. So we just click on each column. So left click on the column and right click on the column, and then we've got a menu here. And we're going to use date time column. And you can see that there's a number of options here. Day column for this one. Right click, month column. Right click, year column. Right click again. Time column. That just means we've got the right entries for the date. And then the data series. I'm not going to use date and time. We're just going to set the data column. And the next thing that'll pop up, it will ask for the part names. So the part names give you the address of the container that it's going to. And we can put anything in there that we like at the moment. I'm just going to put some values in there. The part C is a precipitation increment. It's already set up as 1 day. F is kind of free form. I'll just put something in there to tell me what's going on here. I'll put them in its lowercase. If you tab across, it'll change it all to capital case. It only works in capital cases. Needs the units, which in this case are millimeters. The part name is per cumulative. And then we can press the import now, which will then import the data into there. Before I press this, it's important to know what's going on. It might seem that nothing happens, because now it will ask you, do you want to close the import table or return to table? Actually, we're going to close the table. This is basically asking you if you're happy with the way you've set the data up. And if you are, you don't need to go back to re-enter those values. So I'm going to close that. And now we can see that the new series has been entered in the DSS file. What I normally do then is select it. There's a couple of ways of selecting it. We can highlight it. If you double click on it, it'll come down in the selection at the bottom. We can click on several. Records if we want and plot them all. Going to highlight it. This button will plot the series. I always like to have a look at what I've imported, and then we see what we expect, which is a nice long time series from 1889 all the way to 2000. You might want to have a quick look at some of these events, big events that are happening in on the record there. You can also take a screenshot of this or plot this out if you need. And also this tabulate button will tell us the values. We can have a look in there. You can even edit these values if you need to by turning on the allow editing button, and then you can get in there and mess around with those if you like. A few other options begin to appear. We can start to act on this through the toolbox. So you can access the toolbox through the menu or through the math functions here. Some really cool stuff going on. General stuff, unit conversions to set types and so on. Time functions, this is very useful for picking out the maxima. I've got maximum for period, and you can go to a water year here and pick out the maximum rainfall, the maximum flows in a water year, which is you're going to need for your flood frequency analysis. Now, if I just do this for the maximum for year, what it will do, it seems like it won't do anything, because all you do is press the button and it'll say compute complete. And then it'll say, do you want to save the changes? And you'll say yes, because I want to keep that stuff. And then it'll add another series in. And in this case, it's put the suffix on, WY for water year, and it would have picked out what those maximum were for each of the containers. Another useful tool under the time functions would be irregular to regular. So quite often we've got irregular series and we want to convert them to regular series. And of course, you're going to need a regular series if you want to do a flood frequency analysis, which you can access through the statistics. So we've got duration analysis and a frequency plot, depending on what the data is, of course. So that concludes the live demonstration. This is what happens when you have when you put null values. I've got NaN here. Here's the text file, which is the source file. Again, I've created that using a spreadsheet, and I've just copied it into a text file. I like text files because they're kind of immutable once you create them up and set them up. And this is how DSS View will read it in. What it's done here is it's gone down the record until it's found the first real reading, which is on the 2nd of January, 1889. And then it's done all consequence readings after that. You can see that if you've got NaN there, it'll just do a blank. So coming back to those quality codes, if your rainfall data is not exceeding a particular quality code, you can put a code in there, and DSS view will read it as a blank. It might cause some other programs to blow up. There's a bit of a discussion about whether that's a good thing or a bad thing. I think it's actually a good thing, because if it makes your program die, then hopefully you'll go back to the data and poke around with it and find that perhaps you're trying to do something with a nothing rather than do something with a real record. How do you reference HEC-DSS from other programs? It's good to see a lot of HMS and RAS units on here. Basically what we do is we're going to select the file and the path name. You don't have to rewrite the files. HMS, there it is. So in this case, we've got a hydrological model, and it's under the DSS. If you want to reference a time series, it's under the DSS down here in the time series. You'll see that I've selected single record DSS here. Browse the file. When you open the file, it should, yes, come up with something which has got lots of path names. And of course, you can select that just by clicking on it and saying select path name. You can also put wildcards in these, which is useful for when you've got things that don't quite fit your data window. So you can substitute part of the path names, and be a little bit careful about that with the asterisk. So that gets the gauge record in there, and then you can reference the gauge record from as an observed flow. You see that I gave it a code up here as an observed flow in whatever component of the system that you want to apply it to. So that's a way that, and if you want to import the rainfall, you do exactly the same thing with the DSS file. And also when you're exporting your results, you'll see that there's an option. I'm not quite getting it. Yep, there's an option in here for the output DSS file. Same thing happens again. You can select the file name, and it'll output your results into that particular file. The DSS files they'll start to blow up when you get over, I think it's about 2 gigabytes on my system. So when I was looking at that long-term continuous simulation, I really had to cut it up. I was limited by the size of the DSS file, and so I had different DSS files for each of them, and then we can merge the results from all those DSS files using the copy out function. One little quirk of the system is that if that DSS file does not exist, it won't tell you, but what it will do is then default to writing the results back into the DSS file in the project. So it won't write the DSS file results, the thing that you've specified there, because it doesn't exist. Yeah, so you've got to create that DSS file before you reference it in HMS. The story with RAS is very similar. It's just a RAS project I'm working on at the moment. We can look at the study date, the Untitled study flow data, you look at the flow hydrograph. And up to now, you know, we can put in a lot of flows in here under the enter the table, but you can set it up so it can read the DSS file. Now this is useful if you're going to rerun the HMS project or your hydrological model before rerunning your hydraulic model. You don't have to input this stuff all over again, because it will just remember the references and overwrite the data, use the data. We also have the DSS button over here. This is where the outputs go. So you can see again, we've got the DSS file, we've got part names, and so on. So, and the kind of filtering system that we saw in DSS view. So this is how you can access the information through RAS. It's exactly the same information that you get in DSS view. So again, create the DSS files before you try and write to them. If it does not exist, the program will just change the reference to a default, which means that you can actually, if you've got multiple runs, you can actually blow up that file by trying to pack too much data into it. Part names can include wildcards in some of the parts. Can you reference DSS from non-HEC programs? Well, there is an API on the on GitHub for the Vortex tool. I refer to Thomas Brower, who wrote it. I haven't looked at that yet, but I have used Vortex. How do you manipulate data in DSS view? Again, you've got to understand some of what it's doing. So there are a number of functions down here. When you click on a series, you can get a menu of results. The edit, be careful about how to do this, because what it will do is edit the whole lot. And if you put in different part names, it will write a new series, but it will retain the old one. So it's not, what it would do is actually duplicate the series. Yeah, we looked at the time window under display time window. Yeah, that gives you a year. We're dealing with real time, and note that, and this is a bit of a cryptic problem if you tried it, that midnight, say on the 1st of January, is not at 100 hours, it's at 2400 hours on the previous month, December the 31st. Now, because DSS works with containers, what it will then do is create a container for December, and with only one entry in it, which is the one right at the end. If you're stitching together a whole series, bunch of series, and you're doing it in time order, you'll create the series for, say, the year 2000 up to December. Then you create another series. You'll import a series from 2001 from what you think is January. But remember, it's got a blank December period, so it'll overwrite December from the previous year with a bunch of blanks. I found that when I was stitching those series together. Some of the more useful functions, if you get things a little bit wrong, is the rename function. This is where you can rename the part names. So what it will, so if you made a mistake in your entry stage when you're putting the data in, you can actually use this as a rename. Duplicate does exactly what it says. It will create a new record. Copy will actually copy it to another DSS file, so you can export from one DSS file to another. There are further functions, and I'll just mention them at the moment. There's some basic statistics. Irregular to regular is really useful. Duration analysis, you can use that. It's really rapid, but you need a regular series. It does some frequency analysis. I haven't really experimented with those a lot. Like I said, I would use SSP. SSP has got some higher functionality in it. So if you want to do your flood frequency analysis to log Pearson 3, you can put in multiple grub spec tests for influential outliers. You can put in different options for the plotting position and so on, and different entries for your confidence limits. So for more advanced functions, I would use SSP, but SSP needs to read the DSS file. But you can use DSS to pick out the yearly maxima in a time series to do your flood frequency analysis. It's fairly rapid. Gridded rainfall. This is the exciting new development. It's so exciting that, or so new that we're using beta versions. I'll refer to Matt, as I was finding out this morning about RTS. So the Vortex tool, what it does, it's been recently written by Thomas Brower. It imports net CDF format into a DSS file. You've got to use UTM projections. DSS View 3.01 creates the DSS file and accesses the data. It's pretty similar to 2.0, but 2.0 will not do the gridded data. And if you want to use the gridded data, you've got to have HMS 4.7, which applies gridded rainfall through the grid to the catchments. So the workflow looks something like this. You've got to create a DSS file with DSS View 3.0. Use Vortex to inject the grid into a DSS file. Vortex will just navigate to the net CDF file. It'll ask for a projection and so on, or it'll ask to reproject it, which is optional. You've got to use UTM projections, Universal Transverse Mercator, I think it is. And what you'll see is a code there. It's the UTM. It's zone 55, not latitude and longitude as I thought, and it's south if you're using Australia. Of course, Australia's several zones, I think 50 to 56. And then you reference the grid from HMS using wildcards, because when you import it into DSS View, what you'll see is an entry for every day. You see each of these D parts and E parts, has a specific value associated with them. You need the wildcards to say pick all of the D parts and pick all of the E parts. On that, when you press the plot button, you'll get a plot looking like this. This is pretty cool. That's all the rainfall that happens on that 24 hours on the 31st of December 2019, for instance. And this is from the silo. Silo was free and available, and it's got gridded rainfall to 1889. Okay, there's questions about the quality of the data at that time, of course, but the fact is the technology is there. We can use that. We can use this downloaded data set, or perhaps another data set, to actually put gridded rainfall on whichever catchment we like in that in Australia, as you can see. What does it look like when we get to HMS? Well, HMS has got some really cool functions for catchment delineation and so on. You can also generate catchment. I've done this from the SRTMH grid, which again is available online for this large catchment. HMS will cut it up into catchments and reaches and so on. What it will then do is that you then create a grid which overlies those catchments, and HMS will apply the rainfall through the grid to the catchments. So you've got spatial variation in the rainfall over each subcatchment and over the whole catchment. The results will look familiar to those of you who know HMS. We've got on this screenshot here, we've just got the precipitation on the top and a hydrograph coming out of the bottom. And you can look at what's happening at the gauges with real gauge data. Now, because this is a large catchment, it's several day response time, so we can use a daily time step. Now, this is straight out of the box. This model needs a bit of refinement, but you can see that we're getting fairly good agreement already between a real event, which is in black, and the computed event, which is blue. And of course, you go through you can use the optimization tools in HMS then to calibrate the model and try and move the blue line towards the black line. And you know you've got a good model then when the blue line is pretty well coincident with the black line. And the time units along the bottom, by the way, are days. Now, I wouldn't do this with a smaller catchment, of course. With a catchment with a response time less than 1 day, you need a lot more resolution in your rainfall data. The program will just simply flatten out the rainfall and average it over that 24-hour period. Some concluding remarks then. So DSS is really useful for getting into. It's a very powerful storage data system, provides interface between the different programs. It's a database. You access it through the program DSS view to manipulate the data. You also access it through your HMS, RAS, and SSP. DSS view has got lots of useful features for manipulating the data. You should be able to do all that stuff with DSS view rather than a spreadsheet. And as I say, spreadsheet's got limitations. You can't do dates before 1900 in particular. Future HEC programs will increasingly rely on HEC-DSS. So if you want to keep up with HEC, we've got to understand DSS. Finally, the future is gridded. This is my thoughts about this. The implications here are quite profound. The traditional way of doing things was large models was to create, spend money on and a lot of time creating a very large model. Brisbane River Catchment Flood Study, I think, took $2 million and several years to complete. You're never not going to need quality control and peer review and checking in some of those decisions and so on. But you can actually assemble the data very rapidly. We now have terrain data online, which is free, SRTMH, in some cases LiDAR. We now have the gauge data, which is online and is free. We've got the rainfall online and is free in gridded format. So the whole game now changes towards how can we assemble that information into a working model quite rapidly. And I think one of the prospects is what I call on-demand modeling, which is instead of having a large model of a catchment, which is very expensive and very complicated, you'll have a client which says, I've got a bridge at this location, what are the flows? And you knock up a model very quickly to respond to that. There's this whole thing about accessibility. There's other future prospects. We can have a grid of the variations in fractions impervious across the catchment, or grid of the variations of how vegetation responds seasonally to winter and summer seasons and so on. So this really does open up a lot of potential in terms of the kinds of problems that we can address. And that concludes my presentation. Thank you very much.
All right. Thanks, Martin, for that, for stepping through that. I know that was compressed from a longer presentation, so great job on packing all that information in. Matt and Karl, if you want to come online, it'd be great to hear from you. I guess 2 items. Number 1 would be, can you tell us what's coming next? And maybe even go back in time a little bit and tell us where this all came from. I would be interested in that. That would be a question I would have put on the Q&A line for those who have been involved since I think the 1970s on some of these things. So I'd be curious where it all came from and where it's heading. So we saw where we're at from Martin. Great presentation on utilizing the data right now. Where did it come from and where are we heading with it? And then after that, we'll get into some of these Q&A questions that I see you've answered already. But yeah, in the meantime, let's just get Karl and Matt on the line. Tell us a little bit about the history and where we're heading from here.
I'll just talk 1 second, then you go, Matt. I'll just mention we started in Fortran. We were in Fortran and with not very much memory. And that's what was a big deal, to make a database that didn't waste memory and that could do a lot of data and go fast. And so we still have a little bit of Fortran roots. Go ahead, Matt.
All right. Well, yeah, and first off, actually, so I was, while Martin was busy, trying to squeeze all that information into a short time, I was, chatting on the side with his old friends Tom Brower and Mike Bartles, and they're full of love for you back, Martin. They have a lot of respect for you and wish you well, and thank you for the kind words. So back to Cray's question. Yes, DSS has been around a long time. So the history lesson is that back in the days of Fortran and mainframes, we didn't have a lot of the tools that we take for granted now. They're on tap. We had to make our own. And as Martin was explaining, the Corps of Engineers in the United States was busy, designing reservoirs and, massive flood control projects and such, and needed to make all these things for our own purposes so that we could do just like he was doing and stitch a bunch of models handling different types of hydraulic and hydrologic analyses together so they can hand the results of one off as the inputs to another. And so it's the purpose of DSS originally has always been sort of a lingua franca. Is that a terrible pronunciation? But just as a way to exchange data between models. And so even though Martin was trying to keep things simple and high altitude, I noticed in the chat questions that there's a lot of interest in exchange, interoperability between DSS and other data sources. So I think even that could get pretty complicated pretty fast. But I'll just point out that DSS has an API. So if there isn't a pre-made plugin or something like that that works with NetCDFs or whatever it is you're dealing with, you can almost always get there by scripting something up. And even more flexibly, like Karl was mentioning, we provide the DLLs and .lib files if you're in Unix. So that, if you're coding your own C program or whatever it is, you can link against those and still do the reads and writes with whatever compiled environment that you need to work on. So you can always get there from here. And the big thing that Karl has brought to us in the last couple of years is following through on a project Bill Charlie, who was the father of this DSS a long time ago, and now sort of hanging with us as a rehired annuitant for a while. But Karl was followed through with this new update, the DSS version 7. And so I think you'll see in the chat said, oh yeah, Martin won't be limited by those 2 gigabytes anymore. There's a lot of improvements there, and rather than get into details, I'll just throw a few links here in the chat. And I encourage you to follow up if that's of interest.
Great, and I think just so that any links you put in the chat, we can put on the YouTube description as well. A lot of people will be watching this on YouTube afterwards. So yeah, post those into the chat, and then we'll have those posted in the description of the YouTube video as well for people to download.
Can you tell us about RTS?
Okay. So there's a couple of other HEC software products that we would like to take the opportunity to point out to you. And I was fishing around. Karl, you could put the link for the oh, never mind, I found it. There's the other link,
Okay.
the actual link, the DSS libraries and documentation for how you program against them. There is that last link. So yeah, the 4 links that we shared in here, the DSS libraries is that last one, and the documentation for coding against them. The DSS view, the tool that Martin was mostly working with, including the scripting API, so how you can automate a lot of those functions. And then just minutes ago, we finally got the HEC real-time simulation program posted on our website, version 3.1.1. And that is officially released. You can download it now. And within it, you will find the whole suite, well, almost the whole suite of HEC programs. You'll find HMS, I think we have 4.5 in it, and RAS 507, and DSS View. What is this one? DSS View 3.0, January 2019, it looks like. So if it turns out that you have bugs to report, please pass them along. The contact information is in the website. And then finally, there's an awful lot of interest in the gridded data and meteorological imports. So besides Tom's Vortex program, or whatever scripting sort of things you'd like to do with gridded data in DSS, we would also encourage you to check out the METView program, which is a relatively new model that is very powerful for you want to move this storm here or there, or scale it up, or rotate it around and do that sort of thing. Also, it provides a lot of built-in functionality for importing, exporting from DSS to common formats, and it has a batch mode, so you can automate that on your systems as well.
Those questions that you have answered, Martin, Karl, and Matt, along the way, if you want to just take 1 or 2 of those that you think would be most relevant to the general audience and just highlight what the answers are.
I don't know, Karl, any of these catch your eyes you want to say more about?
I'll mention the one about the file size. How much data can you put in a file? And the 8 gigabytes has been the hard limit. And depending on your machine too, you might not want to go that big, and you have to kind of manage things. But in the newer version of DSS, you can go essentially whatever your operating system can give you. And we've tested those up to 125 gigabytes. And so the file size, it's essentially the file system itself, DSS.
I'll just take that question on the catchment terrain series, terrain files and so on, and where you might be able to find things for Australia. The go-to site for terrain data for me is the Elvis Elevation Data Portal. That has listed, I think, all of the publicly available information for Australia. The SRTM, the Shuttle Radar Transmission
Topograph.
Transmission, yes, sorry. That's a 30-meter grid that covers the entire globe. Obviously, it's not as accurate as some grids, but it's pretty good for catchment delineation on large models. That will cover the entire Australian continent. The Elvis website also has available LiDAR, and sometimes you get that down to 5 meters or even 1 meter grids where it's available. Victoria seems to be on its own in some ways, that it's not, the data for Victoria is not available as it is in other states. Unfortunately, I know it's there. I think it's under license, so therefore you can't download it for free. Also mention that if you want gauge data, there are various portals for various states. The one I go to is the Water Data Online, which is Queensland. Even though it's Queensland, it's got all the gauge data for all the states everywhere in Australia. And those are time series data. And what I would do is download those series and import them to DSS. The silo is Silo Long Paddock. That's a gridded rainfall series, which has been interpolated from all the gauges since 1889. Of course, at 1889 we have fewer gauges than we do now, and so we can talk about the quality of that data. Spot checks on specific gauges. When you get a grid point over a gauge, you get a very good match with the gauge data from what I've seen with the silo. So Silo's done all that interpretation for you. The reason I use it is because it's already done that interpolation and it's consistent. And it's done it consistently. It is daily, so you can only really apply it to large catchments. I think the BOM is doing something similar at the moment. So
and I think those data sources, I think I saw about 3 or 4 questions come in about data sources for where you can get gridded rainfall, where you can get the gauge data, and where you can get the terrain data. So we'll try and pop a few more links in there. You know, this may be specific to Australia. There's plenty of them in the US as well. I saw one question about Canada. Your individual jurisdictions may have individual websites that we could post in there as well if we're aware of any. One question I wanted to bring up, again, because there are a lot of HEC-RAS users on attending today. I know somebody asked about the statement in the manual for HEC-RAS, which is talking about a plan to convert all the binary output to HDF, which I think is the hierarchical data format. Anything you want to comment there on HDF versus DSS formats, Matt or Karl, on where things are heading down the road? So
Actually, Karl would be the guy that tells you like real useful technical details, but just from an overview perspective, I don't believe that we're going to be using DSS format for storing a lot of large RAS output. It's mainly I think we'll have a different storage solution for the HDF5 that works in a complementary fashion with the time series data in your DSS file.
Yeah.
Anything else you'd like to say about that, Karl?
That sounds reasonable. Yeah.
Yeah, and again, data sizes. I mean, sometimes I run these jobs. I need a separate external, 2 terabyte drive for each of these big jobs that I'm working on. And so the data storage, when you think about this, where things are heading with gridded data, you've seen some of these gridded things, especially those who have taken some of the HEC-RAS courses through the Australian Water School or even the HMS ones. We get models with hundreds of thousands of grids, and now instead of each grid, being broken into subbasins, every single computational grid, in the future now is going to have its own time and space, time varying or temporally varying roughness coefficients and hydrographs. I mean, instead of basin-based hydrographs, you've essentially got 100,000 different hydrographs coming in as this storm moves from one end of the catchment to the other, and they behave differently. And we want to be able to, eventually put these into Monte Carlo analyses and look at statistics for these. I mean, what we're doing now compared to 10 years ago, if you project that into the future, another 10 years, and how big these data sets are going to be, this is why we're doing this webinar, for the industry, to show that wrangling this data, as Martin called it, is highly important. So we've got about 5 minutes to go. And again, this is kind of a free-for-all on the questions. I see if some of them have been answered, some of them are still open. Let's just call a few of these out. Martin, you talked about the containers, and then and whether some of these other programs can read the containers. I see one here about HEC-RAS. You want to just, that was one that hadn't come up yet. Matt or Karl, you want to talk about ResSim and what that does and how you might be working with that one?
Well, I think we're unfamiliar with the term containers in this context. We're suspecting it means something very specific, but I'm not sure what that is. Yeah,
that was Martin. That's the term that you use. You might want to have a look at that question, Martin, online, and then maybe look at that real quickly.
As I understand it, the DSS will collect the data and put it into containers, which are assigned according to, say, your month or your year or your day or so on. It can, as I say, it can get a bit confusing if you're merging series. One thing to realize that's quite important about DSS is it won't necessarily delete your previous results, it will just overwrite stuff. Sometimes you. So if you've got some series in there, and then you export a new result into that same, using the same part names. Sorry, the part names are the address of the container. Then it'll just add those part names to the container, so you can have relics of your previous runs in there if you're not so careful. Dealing with time is you've got to be careful about that. As I say, you can overwrite a series in December with a whole load of blanks if you're not careful. And I was finding that, and I was stitching all these series together. I was looking at the resulting thing, and it had, it looked like gaps. Somebody with half their teeth knocked out was the graph, and that was because I was writing blanks over December. So you've got to be careful about how you merge series. I'm not sure if the new versions do that, but the reason it does the containers is to do with saving space, as Karl was saying, I think. So you've got a very efficient system, but it's got buckets in it rather than individual values.
So I think, Karl, when Martin's talking about containers, I'm translating that as blocks or path names.
Yes.
And so just to go very high altitude, refresh. So DSS is it's a database format, but it's a fairly simple one, right? You've got these discrete, self-contained little files, kind of like a DBF file, if you remember those. And you can carry it around, and it's got everything you need. No external schemas and user accounts and whatnot that you need to tend track of. And as Martin mentions, within that DSS file, there's all these path names or containers. And they are, for reasons of storage efficiency, constrained within a certain range of actual bytes. And if it's monthly data, it might be 10 years of it in one block. If it's 15-minute data, it might just be a month. And if you're copying these around, that puts a little burden on you to keep track of, where you've got breaks in your data and, what you're clobbering. And in DSS, everything is basically designed to work if you've got a time window defined. Then the DSS libraries take care of, it makes you able to ignore, those separate blocks.
Good. I think that's a good overview. I'm glad you hit that. We are just about out of time. We'll have some closing remarks, I think, from each of you. But as we're doing this, let me just preview a couple of other things that we'll be doing in the future. I think, I don't know if that comes up there. We are going to get into Python scripting in the future. These are things that, people get geeked out about, but it's very vital for where we're heading. You've seen some of the just genius things that are going on over at TwoFlow over the last couple of weeks, where we're heading from here. Getting into the coding and being able to run some of these Monte Carlo analyses and figure out, many iterations of these storms so that we can better prepare for them. That's what this is all about. So I appreciate Matt and Karl, you guys getting on from the other side of the world here. Martin, thanks so much for that presentation. Closing remarks, start with Martin, and then we'll go to Matthew and then Karl.
Yeah, thanks, Karl. Thank everybody for tuning in and listening. This requires, I think, it does need a change from our traditional approaches. We're now getting the computers to do the work for us. That we can assemble the data very quickly. The availability of the data online is quite astonishing now compared to what we had maybe 20 years ago. And I think more and more we're going to see on-demand modeling, which is assemble the data and give me an answer rather than let's create a model and preserve that model and curate that model for a long time. The important thing is to get the data right. There's a question there about accuracy. We can always talk about the accuracy of the data, but now we've got the technology to put it all together. So I think this is this really is we're pointing towards the future in this, I think. Thank you.
Yeah, great. Thanks. Over to you, Karl.
DSS has a rich history and a rich future, and look forward to an updated version of DSS View in the next coming year.
Great. Matt?
For the international perspective,
freeloaders. You can call us the international freeloaders if you like.
Well, no, not so much that. But DSS, the gridded the coordinate systems within the gridded records tend to be very U.S. centric. UTM is the main thing that helps with international usage. There are other ways to do it, but it gets more difficult. And then I would also mention that there are interoperability tools in like that RTS package, for instance. There's integration tools between DSS and Whiskey, which I think is popular in a lot of places.
Good. Excellent. Well, I think that wraps us up for the day. Then thanks so much. You'll see a slide here coming up. You will get a recording that will come to everybody who registered, and you will get a survey. Again, please help us with that survey so we can guide future content. And then look at what's coming up. On-demand courses, live courses that we'll do, obviously not face-to-face, but live being live Zoom and other platforms that we'll use to really bring you the same products that we were bringing you face-to-face before in our new COVID world. So look forward to some of these extra topics coming up. Python scripting, sizing your riprap based on hydraulic model results, how to optimize your 2D model cell size. The guys from 2Flow are going to help out with that. That's awesome. These are great topics for crossing boundaries between hydrology and hydraulics. Watch out, I guess one final message, watch out on your DSS files. I've heard horror stories of people getting burned by saying, I didn't model this and that, and it's actually saved there in your DSS file. So watch out what's in there when you're running HEC-RAS and other programs. Sometimes it's got a history of what you've done, and you might not realize how much information is in there. Very powerful tool. Thanks so much, guys, for getting online. We look forward to your attendance at future webinars. So with that, we'll sign off. We'll be in touch on future webinars. See you online. Bye.